Hi everyone. I will be asking the question whether can there be a unified spectral model for black holes and neutron stars. There have been numerous attempts in unifying different spectral and timing properties of different compact objects, namely black holes, neutron stars, and white dwarfs. We will be focusing on the similar of these two types, black holes and neutron stars. I'll talk about why we focus on only these two objects, what are the similarities, what are the differences, how do we go about arriving at a unified model for this thing throughout the presentation. So this is basically for the session E1.8. This work has been done with Professor Sandeep K. Chakravarti at SN Bose National Center for Basic Sciences. For further details about the work based on which this poster is made, you can check out my website, which is on the right side of the screen. You can also contact me on Twitter for small queries and over the mail for larger queries. So what basically do we see in the spectrum? So both black hole and neutron stars, stellar mass black holes and neutron stars, they are very active in X-rays. They exist in most of the X-ray binaries that we see, as in there is a companion star and the X-ray component comes from the disk or the star's surface for the neutron star at least. If you look at the left panel, you see the typical Z source, Scorpius X1. It has three typical states: the horizontal, normal, and flaring branch. You see the spectral variations there. There are two major hump or components there. One of the power laws change quite a bit in the flaring branch. If you look at an atoll source such as this 4U1705-44, you can also see there are four types of the spectral states. The island and the banana states are present there. You can clearly see if you use any phenomenological model or model based on Comptonization components, such as, let's say, CompB, for example. You can see the iron line is present there. There is an emission coming from the surface of the neutron star, as well as one component coming from the Comptonization of the disk. If you, for instance, look at the spectra of a typical black hole candidate, let's take the brightest one, Cygnus X1, you can see that it can either be soft photon dominated, which is a soft state, or be hard photon dominated, the hard state, or it can be in between many of the intermediate states. So you see, and the activity domain is basically in the soft to hard X-rays, can go up to some MEVs as well, depending on your instrument you're measuring it. Essentially, they both are active in the same spectral energy domain. They have similar variations, although there are more complexities present in the neutron stars cases. Now, what do we know from a theoretical point of view? What do we know about this system? So we know that the only difference between the black hole and the neutron star is the presence of the hard surface for the neutron star, which mandates the matter to stop at the surface with almost zero radial velocity, and it would pile up, the density would go up, and there would be black body radiation coming from the surface. Now that radiation can act as a seed for Comptonization in the Compton cloud, which is present near the star surface, and can have a magnitude of effects in different ways. Now, for black holes, we do have a solution which addresses spectral and timing properties simultaneously, namely the two-component advective flow solution. It was given by Chakravarti and Titochuk in 1995. This is a schematic taken from 2015 review article. Here, the components are the disk, which is a viscous component along the equatorial plane, supplies the seed photon in black body. You have the halo component, which is shown in green here, which is a subcapillarian component. It is an advective component, not so radiatively efficient, but it undergoes a shock, puffs up after the shock in the post-shock region, and provides the Compton cloud, where Comptonization takes place. Combining these two components, you can actually produce all the spectral variations that is required for the black hole binary systems. Here the parameters are the two accretion rates, the location of the shock, as well as the compression ratio, which gives you how strong the shock is. Now, in order to check whether this sort of a system, this TCAF geometry or the TCAF paradigm is applicable for neutron stars or not, we take a twofold approach. We study the timing as well as spectral properties. Now, in timing, what we find is that we did a twofold study. I'll go through the timing first. So what we do is that we take a time dependent code. We use a smooth particle hydrodynamics code in which particles are injected in forms of torus, and we solve for the conservation of mass, momentum and energy in this RZ plane. This is a neutron star sitting at the center of the plane. Now what we find is that for inviscid flows with low angular momentum, it forms multiple shocks in the flow. This is the outer shock, this is the inner shock, and you can see instabilities forming in between. You can also see the generation of outflows. Now when cooling is present in such a system, these shocks oscillate and they can actually form all the variations in the power density spectra that is seen in observation. You get the low frequency QPO, you get the higher or kilohertz QPOs as well as the hectohertz QPO. Now when you add some amount of viscosity in the matter, you can see the formation of a disc-like structure out of a subcapillarian flow. It also forms different transition layers in the flow, which are previously reported to be forming from a capillarian disk. So here we show a generalized mechanism of forming transition or boundary layers or spinning up the neutron star depending on how strong the viscosity is in the system or the flow. Now when you have a differential viscosity, you can actually see a disc-like structure forming on the equatorial plane, and the subcapillarian flow, the shocked accretion flow, is also continuing away from the equatorial plane. So you can actually see the formation of a TCAF geometry. So we can understand that these four parameters of the TCAF geometry can be applicable to any model which is stable for this sort of system. Now what do we get in the timing spectral properties? So in order to check the effect of Comptonization, which is a non-local process, we use Monte Carlo simulation where we inject photons from both the disk on this side and the neutron star normal boundary layer from this side. So this is a 3D code. This is a cross section of the temperature profile of the system. We take the shape of the send ball to be a torus, which is a a open torus on one end, and after we inject the photons, we let it randomly scatter within the system and finally let it go out of the system, collect it, we get the spectra out of it. So what we see is that when you use this sort of geometry, this can produce spectra which is very similar to what we find in observation. If you let the Compton cooling take place, you can actually see the Compton cloud cools down from a hotter region very close to the surface to the region shifted outwards, as well as a strong cooling of the overall decrement of the temperature. Now if you vary the TCAF parameters, you can see the spectral hardening. Here we show only in terms of the halo accretion, which is an important parameter which gives you the hot electrons in the Compton cloud. And once you consider this stronger cooling, we see the inner part cools down further, the outer part cools down less, and the resultant shape of the cloud turns out to be very similar to what we get in observation. Now here the parameters what we require is the temperature of the neutron star, and we see there is an effective region near the star surface where the cooling is stronger. You can also understand this because of this complex geometry, the interception of photons is very much angle dependent. So not all the photons are intercepted from the neutron star's boundary layer. So when we combine these two aspects and put it into a single model, we tried to do so. So we took the TCAF's basic geometry, the robustness of its geometry on the outer parts, and we included some new parameters which is required for the neutron stars part. So we included the N mole, two more parameters. One is the fraction of photons intercepted by send mole and vice versa, as well as the extent of the inner cloud, which is the transparency factor. How much of the inner cloud is visible to the neutron star? How much of the cloud is effectively responsible for the scattering? If you include these parameters in this system, what do we get? So this is the model that we are talking about. What do we get? So we get, first of all, we get to reproduce all the Z-type variations that were already seen in the Z source called as X1. We successfully reproduce all the spectral variations that we see there. Here you see from horizontal to normal to flaring branch, we generate all the types of spectra there. We also are able to generate the atoll variation, the island state, the upper, lower and left, lower left banana states we can generate here. Now if you go to the color diagram, which is the ratio of different colors, we see that we can actually generate the Z track, the island portion and the banana track, which is also matching with previous observation. So it is clearly, it's not just looks the same, it is actually same Z and atoll tracks that people have reported in observation. So we essentially reproduce both the types of spectra with a singular model which only has 4 plus 3, 7 active parameters. So this is the first time somebody has reported this sort of thing. And what else we get is we check this with observational data. This is the RXT PCU2 spectra of 2 different sources mentioned here. And we see that we get rough estimates of the parameters. We can fit the spectra quite well by varying our parameters. And we have recently reported this to Journal of Korean Astronomical Society. And so what we essentially get out of this is that we can get a common or a unified solution for black holes and neutron star spectra. We can call it TCAF around compact objects, or TACO for that matter. It has 7 parameters as of now. We will be looking into more and more observational cases to see if further parameters are needed. What we get essentially is that out of the 7 parameters, for black holes, you just need to equate the T n mole, FCB and FIC is equal to 0. For neutron stars, T n mole is non-zero because the neutron star's temperature is there. And the rest of the 2 numbers are fractions which are varying between 0 and 1. So this is the generalized model that we are talking about, and we did find this to be achievable. Now here are some references that you can look into. The PDF would be available at the link. It should also be available in the YouTube's description, the video's description box. This is the basic model of TCAF from Chakravarti Tirachuk 1995. This is a recent review by Chakravarti. We include both the papers on timing, one on inviscid flow, one on viscous flows, and spectral papers, one on Monte Carlo simulation, one on this particular model, TCAF around neutron stars. So I hope this is somewhat useful in our endeavor into looking into the commonality of solutions. If you have any questions, please reach out to me. If you have any suggestions, do reach out to me. So thank you for listening.